In the last problem, I gave you a graph, and we used that graph to evaluate certain limits. In this problem, I'm giving you a function, and I'm saying, graph it. There are lots of functions that you know how to graph. So sometimes a graph will be given to you, sometimes you'll be generating the graph. We're going to graph this function, and then we'll use the graph to evaluate the limit as x approaches -2 of that function. All right, and I'll just point out, this is one of our interesting limits because -2 I can see is not in the domain. It would make the denominator 0. So this isn't going to be one of those nice cases where the limit is what I expect and it's exactly the same as what I get. Because at -2, we don't actually get anything. Okay. Now, you learned how to graph rational functions like this. Remember, a rational function is just a polynomial divided by a polynomial. You learned how to graph these in pre-calculus. This one actually is a pretty nice one to graph if I remember that the first thing I want to do, since I'm graphing a fraction, is see if I can write that fraction in lowest terms. I'm going to notice that the top is a difference of 2 squares, so that I could factor that. That's just x plus 2 times x minus 2 over x plus 2. Now I can see there's a factor of x plus 2 on top and on bottom. So I can cancel that. And I'm about to make a mistake. I want you to see if you can catch me. I'm going to cancel that. I'm going to say that's x minus 2. I have made my mistake. If you see what I did wrong, great. If not, pause the video for a second. Think about it. See if you can catch my mistake. Welcome back. Okay, the mistake is that I'm saying that this function here is the same as this function here, and that is a lie. Because this function would be defined at -2. I could plug in -2, I would get -2 minus 2, I would get -4. This function is not defined at -2 because -2 would make the denominator 0. When I say two functions are equal, they have to give me the same outputs and they have to have the same domain. So, when I canceled this x plus 2, which was a good thing to do, it made things simpler, when I did that though, I lost some information. As long as I had x plus 2 on bottom, I could see that x couldn't be -2. Now that it's not there on the bottom to tell me that, it's my job to state it. So this is my simplified version of f of x. F of x is the same as x minus 2, but with this restriction that if I just gave you this formula, we wouldn't know about, so we have to explicitly state that. Now, this is easy to graph. Some of you might have been saying, oh my goodness, we have to graph rational functions already. We'll be doing that later on this semester, but this one's an easy one to do because this is just going to be a line with a hole in it. I'm going to start by just graphing x minus 2. That would be a line whose y-intercept was -2, and the slope is 1. So we'll come up 1 over 1, and then I get to play connect the dots. Now, I've just graphed too much because I included a point at -2, and I wasn't supposed to include that. So, I erase that point, and I replace it with a hole. But what's nice is I know the exact location of the hole. Because when I ignored the restriction and I graphed this, I had put a point at -2, -4. Now I've replaced that point with a hole, but now I can see, as we get closer and closer to -2, the y values get closer and closer to -4. So here's an example where I used a little bit of algebra to simplify the formula for my function, was able to generate a completely accurate graph. Now, It's not completely accurate in the sense that I drew it perfectly to scale, but it's completely accurate in that if I combine the graph with the formula, I can find the exact location of any point or of the hole in the graph, and then I can use the graph to evaluate the function. Pretty cool.